4, 3, 2, 1. Click start stream. No, it was when you see it there.
Oh, sorry.
That's all right. We're still okay.
Well, they're going to see you counting.
They're going to see me counting. Okay, cool.
We're discussing this.
Good start. Hello, everybody. Welcome to the MATH1131. They're probably not even going to see. No, they will see this. Okay.
Yeah.
Welcome to the MATH1131-1141 exam revision live stream. My name's Daniel Mansfield.
And I'm Joshua Capel.
For your viewing pleasure, we will now review the 2015 Math 1141/1131 final exam. We'll do questions 1 and 2 out of this, so this is particularly relevant to the 1131 students, these first 2 questions. And then we'll have a cup of tea, and then we'll do question 4 from the exam. So that'll be a step up, and I encourage you, if you're in 1131, to stick around for that. It'll just be a little bit harder than what you might expect in your exam.
Okay. So I think before we start answering the questions, just maybe a few tips. Now you do have reading time in the exam, so do use that to have a look over the questions and work out where your strengths and weaknesses are going to be, and maybe attack those problems first. You don't want to spend too much time on a question you're just not that sure about.
Can I add one more piece of advice? So the first thing I would do is, as soon as the actual writing time begins, is divide the 4 questions into equally timed portions. So I know it's a 2-hour exam, I know there's 4 questions, I get half an hour each question. And what I would do at the top of the question is I write down when I must finish this question. So right now it is 11 o'clock, and I would, 11:02 to be precise, 12:02, sorry. And I would write 12:32 on the top of question 1. I finish question 1 at this time, no matter what. I encourage you to do the same, because you will devote equal amount of your attention according to the marks this way. And it's a good way, I think, to maximise your marks. So even if you're not done question 1 at this time, close question 1, move on. Cool.
Okay. Right, so I guess I'll start with question 1, part 1. Right, so we've taken the time to write this up to save a little bit of time for you, for your viewing. So the first question I'm going to answer is question 1, part 1, is just to find this limit. Now, this isn't a tricky question. If you look at it, so as x tends to infinity, the dominating terms in the top and the bottom are the terms involving the x. Sine x is just bounded. So, part 1, well, I would do it this way. The limit as x goes to infinity of, well, let's just write it up again. Sine x plus sine x over 2x. So algebraically, just rearrange the function, you get x plus sine x over 2. Alright. So looking at, no, I made a mistake. So, what's the best thing to do here? So I will log this out. This will just become 1 plus sine x over x. So as x goes to infinity, the sine x on x, well, sine x is bounded between 1 and minus 1, and dividing that by x will make that term tend to 0. So you will just get the limit as x goes to infinity being 1 over 2. Sorry, again I made a mistake. I just meant to say that limit is just going to be equal to a half. Right. You want to comment on this before I move on?
I like the way Josh has just put a line through that. That's fine. Don't waste your time making it, Egyptian style, just eliminating all trace of whatever that was. Across through it will do. That's fine. I would have maybe said cross equals a half. Don't waste your time. Just put down the answer.
Right. Yeah, that was a nice problem to just get you started in the mathematics, but this one's a bit longer, as you can see. So we have this function, the definition's given here. And so, well, let's just try and answer the problems they're giving us. So the first problem is to evaluate this function x equals 3 over 2. So part 2, let's just, maybe I might just write down a quick note. So 3 over 2, where is that in this range? well, that's 1.5, so not in this range, it's in this. I could give a reason, since 3 over 2 is greater than or equal to 1 and less than or equal to 3, f of 3 over 2 is just going to be equal to the function using this step, evaluating it at this part of the definition. So it will be 3 over 2 minus 1, sorry, I made a mistake. It is 3 over 2 minus 2 squared plus 1, which is a half squared plus 1 is a quarter plus 1, and I'll write that as a fraction 5 over 4. Alright, so that's the function evaluated at 3 over 2. Now, part B, I'm going to need some space for this. I will have to rub this out just to make a space for this graph. So again, another mistake, make sure you cross out your mistakes and replace them with the correct things. So to make space, I'm going to have to erase this. So let's just get rid of the entire thing. Right, so the range we're sketching this over is from -3 to 3, so I'll just give myself enough space on the x-axis to do that. So be centered around 0. It's marks already, so this is -3 up to 3. This is the x-axis. I'll just call this, well, this will be graphing f. I'll just write f(x). So the definition is just given to us, it's straightforward in the range 0 up to 3, so let's sketch that first. So from 0 to 1, it is just this function here. It's a linear function that starts at 3, substituting 1, it'll end up heading towards 2. So it starts at 3, I'll put some marks on here, and it will decrease down to 2. And I won't make any decisions about that point just yet. This is a parabola. Its parabola is centered at 2, and its maximum will be, oh sorry, no, this is a curving upwards, so it has a minimum at x equals 2, which will be 1. So it's a parabola which minimizes here. If I put in 1, I just get 1 minus 2, so it's -1 squared plus 1, that's 2, so that's quite nice, it actually matches up with this point here, so there's no break in my function. And I'll just have a parabola like that. And if you look at the other end point, you'll get 1 squared plus 1, that's also 2. And I'll just close that point off. Right, so that's what it looks like from 0 up to 3. What about from -3 up to 0? Well, that's where this fact is going to help us. We know that the function is mirror symmetric. So you plug in f of minus x, it's the same as f of x. So f of -1 is the same as f of 1. So it's just going to be a reflection of what we've already drawn. And I suppose I should, I'm going to just completely decorate my graph. And point out that this is actually minimum. -2 and 2. I think that's a good enough sketch. It contains a lot of, shows the function quite nicely. You see it's a nice continuous function. So yeah, that's my sketch. Now let's just answer the final part, part C. Which, if any, of the following exist? And if they exist, state what they are. So first one, what is the limit as x approaches 1? Well, we've kind of already discussed this. It's a question about how much detail I should go into here, so I'm going to just go the lightest detail possible. I'll give you a good explanation. So limit as x approaches 1 from below of f of x. Well, as x approaches 1 from below, the function just looks like this one. So I'll just write that. Limit as x approaches 1 from below of 3 minus x. Well, that's just going to be 3 minus 1 is 2. If we look at the limit as x approaches 1 from above of our function, we get the limit as x approaches 1 from above. Well, in that range, as we're approaching, it looks like x minus 2 squared plus 1, which is just going to be, well, 1 minus 2 squared, so minus 1 squared plus 1, also 2. And because the left and right hand limits are the same, limit as x approaches 1 exists. So I'll just say hence limit x approaches 1 f of x exists, that's what I've just demonstrated, and equals 2. What about the derivative at 0? Well, if we look at our plot, we can see that this isn't going to work very well. As you're approaching from one side, you're going to get well, if I'm approaching from above, the slope is -1. If I'm approaching from the right, the slope is +1. And I'm just going to write down what I said on the page, on the board. So, since the limit as x approaches 0 from above f prime of x is equal to -1, and the limit as x approaches 0 from below the derivative is +1, well, that thing doesn't exist. So, yeah, there's no way to state this value. Yeah, this doesn't work. So, well, since that's true, I would have f prime of naught doesn't exist. Right. So you got criticisms for this final part?
Personally, I think this final part is fine. I've had a few students come up to me and say that they did something like this in their class exam and did not get full marks. And while I personally think that that's worth full marks, I don't want to take any risks in the final exam. Generally, when you're asked for the derivative of a function at a point, you will need to use the definition of derivative of a function at a point. So perhaps I can do just this. I might rub off 2 lines here and just do that right. I mean, to me, this captures everything that needs to be captured in the idea of definition at a point, but I'm just going to recommend to you, you do it slightly differently and use the, and write down the definition. So, thank you. So, at a point, maybe I'll be explicit at the point x equals 1, I'll be explicit. The derivative at x equals 0, exists when the limit of 0 plus h minus f of 0 divided by h exists. Good. And I do need a little bit more space here. So this is the formal definition of limit at a point, and if this limit exists, then you would call it f prime of 0. However, this limit does not exist. Since lim h goes to 0 of f of 0 plus, so this is from below, h minus f of 0 divided by h. And at this point you don't need to do anything fancy. This derivative here is just positive 1. It's the derivative of this function from the left, which you can, and I know I would just say that's equal to 1. Because I know that this function on the left has derivative 1. And lim h goes to 0 from the right of f of 0 plus h minus f of 0. I mean, you could work this limit out. I'm not going to. I know what the derivative of this thing is from the right. This is just a parabola. I could take its derivative just using my prodigious skills at differentiation and figure out that the derivative of this thing is negative 1. And so this limit cannot exist. So f. So if I was doing the exam and I didn't know any better, I would have done exactly what Josh does. This is me just playing it really safe. I know that this is the definition of limit at a point. I'm applying the definition. I'm showing off my skills in a maths exam, and that's exactly what you need to do. You know the definition of limit. Put it down on the paper. Put it down on the paper. I would recommend, if you do get faced with a question about derivatives at a point, use the definition. And then you can speed up these calculations because you know exactly what the derivatives are from the left and the right. Cool. Right, that's part C. Next question.
Right. So question 2 is...
do I do...
Sorry, that's part 3.
Yeah, part 3.
Okay.
Cool. And I'll just wipe that off. Josh and I have been busy pre-baking questions for you from last year's exam. So hopefully this means we can get through a few more questions. Save the trouble of writing everything up. Right. So for part 3 we just have a garden variety integral. It's got a square root x in there. My feeling and advice towards integrals is if something in your integral looks ugly, make a substitution to get rid of that ugly thing. So for part 3 I'm going to make the substitution, let u be equal to the positive square root of x. Necessarily here I'm assuming that x has to be greater than or equal to 0. Cool. With this substitution I might say that du dx is equal to, now let's see, that's 1/2 times x to the negative 1/2. And so I can write this, and that's just 1 on u. So I can write this as 2u du is equal to dx. Good, and now I can make my substitution. Then I1 is equal to, and first of all I'll just write out what the integral is without making my substitution, like this. And now I will make my substitution. And I'll do it in colour just to emphasise what's going where. The important parts, there are 2 important parts. The dx has to become a du. So, and I know how to express du in terms of dx. Du, or 2 times u du is dx. So 2u du, like that. And my root x, that became u. Good. This is a much nicer kind of integral. I can just do this. That's 2 the integral of, I'm going to write as 1 plus u minus 1 divided by 1 plus u. Notice this top is just u. But I'm writing it out in this way because I want to write it as twice the integral of 1 minus 1 on 1 plus u du. Good, and now this should be straightforward to you at this point. This is 2u minus 2 natural log absolute value 1 plus u plus c. It's an indefinite integral, so I get a plus c. I'm putting absolute values around my log. Again, this is me just playing it really safe. When you have an integral, when it evaluates to a log, put the absolute values in. I even know that this is going to be positive, right? Because I'm taking the square root of positive u. I'm leaving the absolute values in there anyway, because that's just how I do log integrals in exams. Just leave the absolute values in. I'm given an integral in x. I'm obliged to give it back in terms my answer back in terms of x. So this is 2 root x minus 2 ln absolute value 1 plus root x plus c. Josh, comments on that?
Oh, that's nice. Yeah, I think this is probably the best substitution to make. There are other ones you can try, but they end up having a bit of extra baggage, which is hard to deal with. For example, you could try u is 1 plus root x. That also turns out to be quite nice. Let's try it, but try it yourself. But I suggest this one had the least amount of. And this one, when you went through it was the easiest one I found. Yeah, this is also a very nice trick, trying to get the bottom and the top so things split up nicely.
Yeah, if you have the same power of u on the top and bottom, then you should be able to split it up this way. So you get some constant and then something with a smaller power of u on the bottom. So you'll end up with the integral of the constant plus what will probably be a log.
Yeah, so substitution definitely the way to go, because I don't see any other way you could have gotten this just by looking at it. All right.
Good. Okay, so next part, evaluate this integral. So sorry, not integral. Evaluate this limit. So you know a few tricks about how to take limits of things, and the first thing that should jump out at you for this one is that as x goes to 0, this top is going to 0 and this bottom is going to 0. So at this point, you should be. Just by reading the question, you should be getting a kind of L'Hopital feeling about this. So, I like to do L'Hopital in a very particular way. So I'm going to let f of x be equal to 1 minus cos of x over 2. And g of x be equal to the denominator, x squared. Since limit So since this is an indeterminate form limit, it kind of looks like a 0 over 0. I like specifying what kind of indeterminate form it is. Sometimes it's infinity over infinity, sometimes 0 over 0. Just some kind of recognition that you're in the ballpark for L'Hopital's rule is what we're looking for here. You need to know that L'Hopital's rule is going to apply. We don't know what this limit is, so we turn instead to the limit of the derivative of f over the derivative of g. Since lim as x approaches 0 of f prime of x divided by f prime of g prime of x. Now let's see, what's this equal to? Cos goes to negative sign, so this becomes positive sign of x on 2 divided times by the derivative, and g of x becomes 2x. And I'm supposed to have a limit in there. Lim x goes to 0. Good. I'll take the constants out. So this is equal to 1/4 limit x goes to 0 of sine of x over 2 over x. This is almost the limit as x goes to 0 of sine x over x, which we know is equal to 1. We spent quite a big deal emphasizing that that limit is 1 during the course. But I haven't quite got that. I've got x over 2 on x over 2. I need this symbol in here to be the same as this symbol down here. So I'll do one more thing. I'll say this is 1 on 8 times the limit as x goes to 0 of sine of x over 2 divided by x over 2. So sine of blob divided by blob as blob goes to 0 is equal to 1. I might even mention that, since sine limit as u goes to 0 of sine of u over u is equal to 1. I'll just say that's 1 on 8 then. Good. So this whole thing is equal to 1 on 8 because sine of blob divided by blob as blob goes to 0 is 1. Hence, so now I need to tie it back to my original limit. So right now I'm feeling pretty happy because I recognize that I'm in the ballpark for L'Hopital's rule. This limit exists. L'Hopital's rule tells you that thing, then that 1 on 8 is equal to this. So right now we've satisfied all the things we need to do for L'Hopital's rule. By lim as x goes to 0 of the original function 1 minus cos x over 2 divided by x squared. Not only does that exist, but it's equal to whatever that limit was, 1 over 8.
Right. So, yeah, I mean, it's a really cute solution. I like the fact we brought in a limit that we should know well. Maybe some of us don't though. Personally, if I was doing this question, I probably would have looked at this and thought, well, sine's going to 0 and x is going to 0. So I would have applied L'Hopital's rule again and gotten the same answer, of course. But it does take 2 applications, so you can prove that this one does exist using L'Hopital's rule, and that then proves the previous one exists using L'Hopital's rule. So I think this is a lot nicer, it's a lot more concise. If you do use this, yes, I think you really should specify that you're using this fact. It's well known, but we don't know if you know it well. Yeah, but no, it's a nice solution. And yes, this, I definitely, if I was seeing someone using a L'Hopital's rule, I want to see that person knows that it's a valid question. Yeah. Sometimes you'll get questions where people will try to apply the rule, but it was never a valid choice to begin with. You never actually had the indeterminate form.
Yeah.
So I like people to state that, and even if it's just for yourself, by saying it, you might catch yourself in some scenarios where you actually were about to apply it in where you couldn't.
So saying it's an indeterminate form, that's probably enough, and that's what the exam solutions say. I like being really. I'm playing it safe, so I'm saying both. I'm saying not only is it indeterminate form, but it's of this indeterminate form. Yeah, I like to be just really, and I personally would have just written that when I'm at home doing this by myself. But because I'm in an exam situation, I'm putting everything out there. Cool. Next question.
So this is going to be our next question. We're going to take these 2 complex numbers to find for us and just try and find all these quantities here. Now there's 5 quantities to find. We'll have to roll our sleeves up to do this, but it shouldn't be too hard. But these first few you can see won't take very long. Right. So, thanks. Alright, so first one, let's just see what happens if we take z and subtract off the complex conjugate of w. Alright. So, part A. I'm just going to rewrite the quantity we're trying to find. It is z minus the complex conjugate of w. So we see that z was defined to be 5 plus I, and we're subtracting off the complex conjugate of 3 plus 2i. Alright, well, that is just 5 plus I minus the conjugate of 3 plus 2i. You just swap the sign on the imaginary part, so you get a 3 minus 2i. Be careful with your arithmetic here. This minus sign, people tend to trip up with minus signs at this point. So I'll get, well, let's see, we get 5 minus 3 will become, actually I'm just going to expand it. So I get 5 plus I minus 3 plus 2i, now there's no confusion. 5 minus 3 is 2, a plus I plus 2i is plus 3i. So yeah, I just quickly double check my calculations. I don't see any mistakes, I think it's fine. So that's a fairly simple one to get us started. Let's try this next one. We need to find the a plus, so this Cartesian form of 10w over z minus 2. So just write this, 10w over z minus 2. That is 10 times w is 3 plus 2i. Let's just double check the question. Don't want to make a mistake at this point. 5 plus I minus 2. Right. So that is, just to write it again, is 10 times 3 plus 2i over 3 plus I. Now to get this in the a plus ib form, the Cartesian form, I'm going to need to realize the denominator. So I'm just going to do that here. So I can realize it by multiplying it by 3 minus I over 3 minus I. So this is a funny form of 1. And if we do that, I get a 10. Alright, so let's just do our product. I'll get a 9. I might just check out the other real term while I'm here. So I get a 2i times a minus I. So let's just write it out as 2i times minus I, so minus 2i squared. You'll have a minus 3i and a plus 6i. And that will be divided by, well, when you take a number, multiply it by its conjugate, you get the modulus squared, which in this case is 3 squared plus 1 squared. So I'm going to get 9 plus 1 on the bottom. Okay, so this number here, minus 2i squared, is plus 2. So I'll just write that as 10 times, so 9 plus 2, 11. A minus 3 and a plus 6 will give me a plus 3i. And everything is divided by 10. Oh no, that's very nice of them. They actually gave us 10s to cancel out. I'm just going to cross those out and say this is 11 plus 3i. So assuming I've made no calculation errors, the Cartesian form of that number is 11 plus 3i. So I was very explicit in my calculations just because there are a few steps where I know I tend to trip up. These terms here tend to trip me up, so I was just being a bit careful with that. So yeah, it's good to know where your weaknesses are and try and tiptoe around them. Okay, so those two were fairly simple. Next one. So we want the modulus of z divided by w all to the power of 8. So I could calculate z over w and then take it to the power of 8. I think there's actually a much simpler way in this case. Thanks. So let's just get rid of this work. Alright, so what we're looking for, this quantity here, let me just rewrite it. So it is the modulus of z divided by w power of 8. Well, nicely, if you take the modulus, well, the modulus of some power is just going to be the power of that modulus. So let's write it as that. So, made a mistake. Oh well. So let's see. Modulus of z over w all to the power of 8. And quite nicely, the modulus of a ratio is just the ratio of the moduluses, moduli, perhaps. I keep doing that. So it's going to be, I'll do it down here, it's going to be the modulus of z divided by the modulus of w, all of that to the power of 8. Modulus of z, I can look over there and see it will be the square root of 25 plus 1, so that's modulus of z. Modulus of w, so it's going to be 9 plus 4 to the power of 8. Let's just simplify that before I try to do any more calculations. I will get 26 square root of that divided by square root of 13 power of 8. Well, okay, they've been very kind to us, and I can see that 26 does divide by 13. Bring those two square roots together. 26 is 2 13s. So this is actually the same as root 2 to the power of 8, which, well, I can bring a power of 2 inside and get 2 to the power of 4. 4 times 4 is 16. So I'm getting that the modulus of that is 16 with a few missteps along the way. I think that was quicker than trying to calculate the ratio. Yeah, so I think I'm happy with that. Any comments on this before I do the next part?
I'm thinking we might leave D&E actually because we're running a bit low on time.
Okay. So yeah, well, if you try D, it's very easy to calculate this number here. If you calculate the product, it is 13 plus 13i. It's just a simple, straightforward calculation, which is nice because it's just a multiple of 1 plus i. 1 plus i, you know, has principal value argument 45 degrees, pi on 4. And then this last part is quite simple once you also know the modulus of that product there. So okay, yeah. So we'll just skip that. Yeah, so these should be fairly bread and butter calculations when it comes to complex numbers.
So I think these calculations won't be too difficult for you, and I want to move on to other things because we have a lot of ground to cover. In particular, I'm noticing on my watch that it is 12:40, and we said we'd finish this at half 10:32. We're going a bit slower because it's on a whiteboard and we're talking to the camera and all that kind of stuff. So I do want to demonstrate the fact that we've probably run out of time already for question 1, and at this point we just close the question and move on to question 2, but I want to do a few. We'll go a bit slower in this case. But, please be brutal and just close the book on question 1 when the time runs out. We're not going to do that. We're going to keep going and just kind of shorten a few things.
Yeah. Just one comment. Make sure you pay attention to what quadrant this number is in. If it's not in the first or the fourth quadrant, people tend to make mistakes. So I do suggest calculate this. Maybe make a little picture. Think about the quadrant. Make sure your answer is consistent.
Always draw a picture. You'd be crazy not to draw a picture in your complex number question. When you're asked to convert complex number to or from polar form, there is a picture in there somewhere. Please put it on the page. Don't keep it buried away in your head. We'd like to see the picture. It will also help you make sure you get your positives and negative signs in the right places. Right, that's not the book I want. This one. Sorry. Good. So this is a very easy question. You just write down what the answer is. This is the typical kind of question that will just make. What am I trying to say here? You should not skip this question. This is just free marks as far as I'm concerned. You want the parametric vector form of a plane that passes through some points. Here it is. So VI. So you choose one of these as your kind of origin. So the plane passes through 114 plus lambda 1 times 211 minus 114 plus lambda 2 times negative 143 minus 114. This is the equation of your plane passing through 3 points. And I'll just simplify it a little bit. That's 114 plus lambda 1 times 1, 0, negative 3, plus lambda 2, negative 2, 3, negative 1. It's easy to see that this is the equation of the plane passing through points A, B, and C. I might mention that lambda 1 and lambda 2 are real numbers. If lambda 1 and lambda 2 are 0, then that bit disappears and I just get point A. If lambda 1 is 1, lambda 2 is 0, I just get left point B. And if lambda 1 is 0 and lambda 2 is 1, I get point C. So whatever this thing is, it kind of looks like a plane and it definitely contains A, B, and C. Josh?
Yeah. So yeah, this is a very simple question. And yeah, you can just answer it in almost one line. So I wouldn't skip that one. Yeah. So there are questions which are really no work questions, or almost no work questions. Make sure you do those.
Yeah, I like keeping this on there because it helps me as the person who's writing it to be very confident that this contains A, B, and C. Second of all, there's lots of different parametric vector forms of the plane. So it helps your marker to understand that you actually know what's going on. So the points A, B, and C and how you arrange them there might be different. Help your marker out to know which combination of putting A, B, and C into this parametric vector form you have chosen.
And that's actually the end of question 1.
No, there's this matrix question.
Ah, so there is.
So if you were running short on time in question 1, don't skip a question like that one I just did because that's free marks. Yeah, thank you. Okay, so now we have a very long question. Consider some maple session. We can just read this together. Here's A. This is A squared. This is A cubed. Here's some other combination of A's and B's. Find A inverse. The first thing I might do, just for my own personal benefit, is write out what this is. And I would write it on the exam paper because this is just my rough working. B is A squared. C is A cubed. And this equation here, well, that's the identity matrix. So maybe I'd write this one out as I equals A cubed minus 6A squared minus 9A. Just translating the maple, which looks weird and alien, into stuff that I understand. So this is nice. This is a matrix equation, I can understand this. Good, so I've gathered all the information that I can find. The question asks you to find A inverse. Okay. Recall that A inverse is any matrix that has this property. If A times B is equal to I, then B equals A inverse. If you have some matrix, then any matrix that you multiply it by, which gives you the identity matrix, is the inverse. So we're not completely on our own here when we're asked to find A inverse. We're given this equation. This is supposed to help us find A inverse. And it does. Here's the I. I know the I is involved somewhere in my identity relation. So I've got an I here, and I can take out a common factor of A out of this equation. Since A cubed minus 6A squared minus 9A is equal to I by Maple session. It's nice to just let everyone know where you're pulling this equation from. It comes from the Maple session. I can take a common factor of A out. A times A squared minus 6A minus 9 identity matrix is equal to the identity matrix. And then I'm in the form of A times some blob is equal to I. This blob has to be A inverse. So A inverse is equal to A squared minus 6A minus 9I. Which I could write down in terms of A, B's and C's. You don't need to see me some of these matrices. Also, because I'm running out, I've basically run out of time, let's say, I would just leave it like that. So maybe I'd lose a mark, but I need to move on. You would certainly write this out as a full matrix, just to be safe. State A, part B. So I don't want to waste any more time doing this. I might lose a mark, I might lose half a mark. I've got to go and get as many marks as I can. So I'm just going to take that risk and move on to part B, because part B is 3 marks again, and I'm going to spend my time on that. A transpose, since A transpose squared is equal to A squared transpose is equal to, well, I know A squared, it's that, is equal to B transpose, and I will just straight up write this down, so that's 14, 5, 25, 4 to 9, 19, 8, 38. Good, so I'm taking leaving my answer like this takes a risk, but I'm spending my precious little time getting marks that I can, rather than just doing some rather lengthy matrix addition on the hope that I won't lose to gain just potentially one or half a mark. Right,
Yeah.
Josh.
So yeah, I think any marking scheme worth its salt would see that this is where most of the marks are going to come from, actually getting to this point in this question. So yeah, I think if you have the time, if you haven't been dawdling and you can just write up what that actually is as a matrix, please do it. Otherwise, yeah, this one, it doesn't take any effort. You should really write that one out.
But there's a fair bit of effort here. I have to add 3 by 3 matrices and multiply things by. I'm just going to leave it like that and take the risk, because it's not worth the time. Right. Now, question 2.
Right, question 2. Please. As per Daniel's advice, we start question 2. Maybe we should just work out when I should be aiming.
I've got 12:51.
51. We have goal. We're a little bit late.
This is just a demonstration of what we think you should do.
Yeah.
Given we're writing this exam on a whiteboard, we're not actually going to stick religiously to this. 12. Oh yes, go on.
So say
1:20, 1:21.
Right.
And be vicious about that time limit. We're not going to, but you should.
So I think you're up first.
No, you're up first.
Oh yes, well, so short I almost missed it. Yeah, try not to miss any questions. That also loses marks. So It's quite a short question, but there is a little bit of work involved in this one. So I'm writing z is a plus ib. I want to try and find the number who squares to 40 plus 42i. So, right, well, so what do we have? So part I. So z squared is a plus ib squared. So if you actually just do the square, you get a squared minus b squared plus 2ab times I. So that is the real part and the imaginary part, and this is supposed to equal to 40 plus 42i. So what do we get by equating real and imaginary parts? We get two equations to use. So we have the equation a squared minus b squared is going to equal 40, the real part. And I also end up with 2ab has to equal 42. Right. Now these are sufficient equations to solve this problem. Everything you need to solve the problem is here. But there is one trick I know which does make this question easier, so I might just show you this trick. In addition, so this is not new information, it's just presented differently. So in addition, if you take a squared plus b squared, that is the modulus of z squared. So that's the modulus of z squared, which is also the modulus of z squared. I know what z squared is supposed to be. It's supposed to be modulus. Sorry, z squared is just supposed to be this number here. So it's the modulus of 40 plus 42i. Modulus of 40 plus 42i is not too difficult to calculate. It is the square root of 40 squared plus 42 squared. Now at this stage I may need to use a calculator, especially for 42 squared. So 40 squared, not too difficult, 1600. 42 squared is 1764. Just add them all up, that's what you get. So I'm looking for the square root of 3,364. If I plug it into my calculator, I get 52. Is that right? No, it's 58. I actually do have a calculator in my pocket, but it's 58, I believe. So you will have an approved calculator in the exam, hopefully. I have an unapproved one in my pocket, but I'm not in the exam, so that's okay. So 3,364. Just quickly take the square root, it's 58, good. Alright, so this is a lovely piece of information because I can use this and my first piece of information to easily find a squared and b squared. So we easily calculate. No. So if I just take this quantity, add it to that quantity, I can get 2a squared is equal to, let's see, so this will be 40 plus 58 is a 98. If I take this quantity, subtract off that quantity, so 58 minus 40, I get 2b squared is equal to, so 58 minus 42, no, sorry, I'm looking at the wrong one. 58 minus 40 is just 18. Let's rewrite that. So a squared is equal to 49. B squared is equal to 9. Hence, well, I know that A will have to be equal to plus or minus 7, and B will have to be equal to plus or minus 3. And now here's what you have to remember. There was that other equation I've been ignoring. So I have 3 equations, but yeah, I need to make sure all 3 of them are satisfied. This last one, this just tells me that the sign of A and B must be the same. So I'm going to have to choose positive 7, positive 3, negative 7, negative 3. Unfortunately, I ran out of space So further down on the board, further down on the page, I will just conclude with the following. To satisfy, what do we have? We have 2AB equal to 42. We choose, we choose the following options. So we have that Z will either be equal to 7 plus 3i or minus 7 minus 3i. Those are the square roots. So those are the square roots. Those are numbers which square up to 40 plus 42i. Okay. Any comments about this?
This is a nice trick. It gives you easy access to B. I prefer to just use these equations and not introduce the third equation, just because I think it's more mechanical that way. So I'd rather have a quadratic equation in A squared, for example, and then just figure out what A is. Because there's no more thinking. It's just solve a quadratic. I don't need to think. I don't need to remember that equation, stuff about signs. It's just, here's your two equations, just solve them. You know how to solve them.
Yeah.
So I prefer doing it that way. This way certainly has its merits, and you know, it's good. It's potentially very fast and good. For me, it's got too many moving parts. I don't want to introduce new equations. I'll just work with what I got.
Yeah.
A couple of people have asked about just inspection.
Yes.
Is that allowed?
Inspection is allowed, but we wouldn't teach you to. Like if Josh and I just stand here and use our fancy math to say, obviously 3 and 7 and -3 and -7 are answers, then that's not very helpful to you. Here are two methods which will always give you the answer. If you can happen to see the answer using just mad skills, then sure, go for it. Here's a method that will get you home every time.
Yeah, I would never have been able to spot this without some fourth method.
Yeah, good luck guessing that.
Okay. All right. Move on.
Cool. For part 2, by the way, I might just show you how to do this question, and I will omit the steps of row reduction with your permission. At this stage, you should know how to do row reduction, so I'm just going to set up the question. Just the next step will be row echelon form. We'll read out the answer. So, as an augmented matrix, I would write this as, so this is question part 2, 1, 2, 0, bar, B1. And then I leave a big gap. This is what Josh showed us showed me in particular. I'd never done it this way before, but I can immediately appreciate the merit in the way he did it. Leaving a lot of space here because I'm going to do some calculations here. This is not a identity matrix. This is just a vector. So don't introduce extra zeros here. Just leave lots of space because you're going to do some working out. 1, 1, -1, B2. 2, 1, -3, B3. And this is the kind of thing that you should just row reduce. As soon as you see a matrix like this, there's no thinking involved. Go row echelon form. That's always part of the question. So this is just muscle memory at this stage. You need to eliminate those terms to get it into row echelon form. And I'll just write out what the row echelon form is. So 1, 2, 0. So these are vectors. I might mention that this is row echelon form, and I will do so by identifying the leading terms. Leading terms are the first non-zero things in every row. So here's a non-zero thing. I'll move across this row and identify this as a non-zero thing. I'll move across here. I don't know if this is 0 or not. That depends on the b's. This might be a leading term. It might not be a leading term. There is a condition on the b's that makes this a non-leading term, which you need for there to be solutions. when b1 minus 3b2 plus b3 is equal to 0. This thing can't be leading. If this is leading, then you've got a leading term in your constant column of your augmented matrix, and that means there are no solutions. If this term is 0, you've got solutions. In fact, you've got infinitely many of them. We'll just say that there are solutions. Here's your condition. We'll put a big box around it like that. The thing I want to emphasize about this question is this way of doing. Put your vector, your augmented vector here with loads of space, because then you can do your arithmetic with the b1s and your b2s and your b3s, and it's just easier to do it that way. Josh, any comments?
Yeah, so obviously you will have to do the row reduction in the exam, and when you are, please specify the row operations that get you there. You always need to specify how you're actually doing these row operations. Okay.
Can I mention one more thing? I would do the row operations one at a time.
Mm-hmm.
I would take it just really carefully and slowly, because when these questions get marked, accuracy of your row reduction is part of it. So please take the time to do it right. You will have enough time in your exam to do the row reduction. It's easy marks if you do it right. So just give it the time it needs, one step at a time. Don't get fancy with it. I'm omitting the steps here because, well, I think you guys can do that on your own, so you don't need to see me do yet another row reduction. But the things I want you to appreciate are this style and how to read out your matrix from row echelon form.
Yes, I guess if you want to see the style again, you can go back to the test 2 preparation and see what I did there. Okay. So next, part 3 is to sketch this region in the complex plane. So it's not too difficult if you. There are a few things we need to recognize. So that first condition, this should seem familiar to you. You have z minus a complex number. I need to rewrite this to get it clear in my head exactly what it is, but z minus some number, the modulus of that whole thing, is less than 1. This will just be a disk of radius 1 centered somewhere. So I might just quickly rewrite what that condition is so I don't get it wrong. Part 2. So I'm trying to look at, one of the conditions I'm trying to look at is when z minus I minus 1, which I'll rewrite as z minus I plus 1 is less than or equal to 1. So this thing here is the, I'll just say unit disk of radius 1. Centered at z equal to I plus 1. So I have a disk of radius 1 centered here. What about this other condition that we'll be considering? So we want the absolute value of the imaginary part of z is greater than 1. I'm going to write it slightly differently. So if z is equal to x plus iy, then the absolute value of the imaginary part of z is just equal to the absolute value of y, and I want that to be greater than or equal to 1. So let's try and sketch up very roughly first what we are seeing, and then also be careful about this word I'll get in a second, the or. Alright, so 1 plus I, let's see, this is real, this is imaginary, point. Thanks. So this will be the point here, 1 plus I, and I am looking, I'm going to do dotted first while I just think about this. So I'm looking at this circle, this disk of radius 1 centered there. I also need that the y absolute value is greater than or equal to 1. It is worth noting that means that either y is greater than or equal to 1 or y is less than or equal to minus 1. So it'll be 2 boundaries. Where I take the imaginary part big enough in a positive direction or with large magnitude in a negative direction. Now, or says I only need one or the other, or in fact both, to be satisfied. So I need to take, this isn't and, it's or. So it can be in this region, or in this region, or maybe it could be in both. So it includes the boundary. So this is less than or equal to 1, and so the equal to part. So this boundary will be along that line, along this circle, along this line. It will also be on this side. Little arrows are just to help me. And this will be below this line, and I'm going to use a different color just to shade this region. So the region is this. I'm missing this gap in the center, which has a bit of a bulge in it. So the region does enter that gap just a little bit. So yeah, it is important to remember that that's an or condition. If they give you an and condition, that would be different. And would just be solely this part here, the top half of the circle. Right, comments?
It's two things, just small things I want to say. If it's not clear to you that this is a disk with radius 1 centered at that point, then let Z do what Josh did for the second part. Let Z be x plus iy, plug it into here, you will discover the equation of a circle in x's and y's centered at 1, 1. So if you're not confident with this, just do this method where you let x equal z equal x plus iy. It will turn out to be a circle.
Right.
Second thing I would have done is just to be absolutely pedantic, I would have put big solid circles at the intersections, just because, I mean, it's hard to fault what Josh did. It's perfect. I would have awarded that full marks. But I don't take any risks. That's not even a risk, but I just do it anyway.
Yeah.
It's kind of like putting the absolute values on your log integral.
Yeah, I guess if this was strictly greater than 1, actually it would still be a solid circle.
No, yeah,
yeah.
I just do that anyway for the intersection.
Right.
It's just 1% things that make sense, and you should always do. Well, I always do. Right. Next question. These are fairly routine calculations. I can be a little bit clever about it. I'm asked for the angle between two vectors, and I'm asked for the cross product. And I know there's, the first relation you get introduced to regarding the angle between two vectors is the dot product one. There's also the cross product one. And given I'm obliged to calculate the cross product, I'm going to go with the cross product one. So I'll actually do part B first, and then do part A. Save myself a dot product, which is utterly trivial, but this is just a little bit less work for me. So part I B. I'm doing B first, or maybe I'll put A. No, I will put B here because I want the person who's reading it to know I'm doing B, then A. So U cross V is equal to the elements of U, 2, 1, negative 1, the elements of V, 1, negative 1, 2. Good. At the start of the course we showed you a way of calculating calculating cross products without using the determinant. Now that you know the determinant, here's an easy way of calculating cross products. You just put the standard basis vectors up here, your vector U, your vector V, and you calculate the determinant of this matrix, which I'll write as E1, so this is going to be my first component times the determinant of a 2 by 2 matrix, which is 2 minus 1, which is 3. For the second element, I get negative 4 minus negative 4 minus 1, so that's, hang on, is that still 3? I might need to go slowly here. So this is negative 4 plus 1. Have I written this down correctly?
I think so.
This is not what I got when I was doing this at home. Negative 1, 2, 1, negative 1, 1, negative 2. There we are. There we are. Good. Right. Let's try this again. Josh, can you just confirm that that should have been a negative 2 there?
Yep, that's a negative 2.
Thank you. Okay, let's try again. So negative 2 plus 1, but negative 2 minus 1 is negative 3. Good. Negative 4 times negative 4 plus 1 is, I'm just going to write it down at this stage. I'm making all sorts of crazy errors. Negative minus 4 plus 1. And finally, the determinant of this matrix, so E3, and I take the determinant of this one, so that's negative 2 minus 1 is negative 3. So I end up with negative 3, positive 3, negative 3, which is 3 times negative 1, negative 1. Good. For part A, I'll note that the length of U is equal to the square root of 2 squared plus 1 squared plus negative 1 squared, which is root 6, which happens to also be the length of V. And since the length of U cross V is equal to length U times length V times sine of the angle between the two vectors, then this thing here is equal to, what is that? The length of that is equal to root 3, and that's equal to root 6 squared times sine theta. Maybe I'll write this out a little bit slowly. That's 3 outside the length 1 squared plus negative 1 squared plus 1 squared plus negative 1 squared, which is 3 root 3 is equal to that, which is equal to that. So root 3 on 2 is equal to sine theta. And hence the acute angle that makes this work is pi on 3. Good. So I saved myself one calculation by doing it that way. You could also have done it using the dot product. Josh.
Okay, so I guess maybe one thing I would have done is just drawn out the triangle for that, just to remind myself exactly which of the two angles it is, because I'm always forgetting. So yeah, the 1, 2, root 3 triangle. It's always
in my mind, I know that sine goes from 0 to 1, so I know that the pi on 6 has to be here, and the pi on 3 has to be the bigger of the two. So that's just how I remember it. I know this is going to be 1/2 or root 3 on 2, and it's the bigger one.
Okay. Right. I guess this one notation thing, try and write your vectors with the fiddles in here.
Thank you.
But, yeah. So yeah, that's a nice thing. You can actually get the information you need for part 2 doing part the second part first.
Sometimes.
Sometimes, not always.
Is it part B now? Is that me?
I
think it is.
Yes, I think that is now part 6. Right.
Thank you. Okay. For part B. Here we have another piecewise defined function. We need to find values of a and b such that f is continuous and find values such that f is differentiable. The first thing I might do is call that thing g and that thing h. G of x. Good. For part A. I'm going to start part A with the definition of continuity. This will give me some kind of framework on which I can hang my mathematics, but you're kind of on your own here for this question. Show the function is continuous. The definition of continuous is a good place to start. When the limit as x goes to 1 of f of x is equal to f of 1, and that's from below, not only does the limit of x, f of x as x goes to 1 have to exist, it has to be the thing that is f at 1. So this limit has to exist and it has to equal f of 1. This is a particularly simple question for a piecewise defined function because this curve here is continuous, this g curve. Since lim as x goes to 1 from below of g of x is equal to, let's see, what is that equal to? As x goes to 1, this is 1 plus a. Equals g of 1. This is a particularly easy limit to find because g is a continuous function. Similarly, lim as x goes to 1 from above of, maybe I'll set that's f of x. F of x is equal to the limit as x goes to 1 from above of h of x, which is equal to, well, h is also a continuous function, so I can just say that this is b plus 2. H continuous. I know what the limit of h is as x goes to 1, it's just h of 1. And to know that, I know that because h is continuous. Good. So the limit, and I might also mention the third item is that f of 1 is equal to g of 1 is equal to 1 plus a. And these three things have to be equal. So when 1 plus a is equal to, well, that's 1 plus a, that's 1 plus a, and this thing is b plus 2. So, what is this? A equals b plus 1. Behold my condition for continuity. I'm going to do the same thing for part B and show that the function is differentiable at x equals a, and I'm going to do it starting with the definition of differentiability. And I might just file that equation away for later somewhere. Right, so for part B. this is the definition for a function to be differentiable at x equals 1. Good. And I'm going to take the left and right hand limits. Since lim as h goes to 0 of f of, and this is the limit from below, as h goes to 0 from below. This is the limit as h goes to 0 from below of g. And I know g is a differentiable function, so this thing here is equal to g prime of 1, since you could substitute in the function there. I'm just going to use the fact that it's differentiable. G is differentiable, and therefore this limit is g of 1. So this whole thing here is equal to, I need a little bit more space. The derivative of that is just 2a. And the limit as h goes to 0 from above of f of 1 plus h of h of x. I shouldn't have used h, I realise now. Using h too many times. Can I call this k instead? K of x plus h. K of 1 plus h minus k of 1 over h. And I know that this thing exists, that's just h k prime of 1, which is equal to b plus 6. So 2a, these two limits have to be, these two, the left hand side limit and the right hand side limit have to be equal, is equal to b plus 6, and it also has to be continuous. A is 1 plus b, is that what I had before?
Yeah, I believe that's what you had, A is 1 plus b.
So I can substitute that into there and find that 2 of 1 plus of b is equal to b plus 6, which tells me that b is equal to 2b is equal to 4. B. We get 2b, take 2 over there, and a is equal to 5, because a is just 1 plus b. Yeah, 2b minus a b, and 6 minus 2 is 4 and 5. Good.
Yes, there is one thing I'm wondering about looking at this. So f of 1 you said is here, so you said it's k of 1?
Yeah.
So that's
assuming
g
it's
of 1. So this is assuming we've actually matched up
yeah.
to make sure that
Well,
g and k are equal.
Yes, so I suppose that's a bit fast because that's happened. I'm assuming it's continuous. It has to be continuous for this to work. So this and this have to be the same. So good, thank you for pointing that out.
Yes, there is something. So yeah, continuity is important here. It's important because you do need to.
Yeah.
Otherwise, you won't have f of 1 being equal to k of 1.
I mean, there's a theorem in the book that just says look at that and look at that, and if provided it's continuous and these two slopes match, then it's differentiable.
Yeah.
I'm just a bit cautious of that. I want to show the fun. I want to use this definition somehow.
So yeah, I guess I just want to point out that it really is important, the continuity. So kind of see, there is one point where it came in implicitly into the argument. All right. I can't really think of anything else to say about that. That does seem right. You are using the proper definition of using this limit. So before we were talking about differentiability, and I made the mistake of not trying to use the definition of a derivative. I did a less than stellar.
No, I disagree. I think your answer is good, and that's what I would have written, except I know that some people will demand this. When they say differentiable, they mean this definition, use this definition of differentiable. So I'm really just covering all my bases. If I didn't know that, I would just use the theorem that says the function's piecewise function like this is differentiable when it's continuous and these two derivatives match. That's the fast way of doing it, and that's 100% what I would have done if I wasn't just playing it safe. And here I'm playing it safe and saying, here's the definition, here's how it fits together.
Okay. Right, so I guess I'll do the next question. Water.
Yeah, it's getting a bit dirty.
So next question I'm going to do is to evaluate this integral. So we've already done one integral in the exam. We did one which they called I1. This is the second one we're going to do. This one, well, it's not really that tricky. What I'm going to use here is the fact that if I differentiate log of x, I like its derivative better. It is actually just 1 on x. So I can use I can use integration by parts to get something which is more something I can just do fairly easily. So what I'm going to do is I'm going to choose to differentiate log of x. That means I have to choose to integrate x cubed. That's not so bad. So let's just set our notation. So I'm going to part 6. Let's let u equal x cubed. Oh wait, no, made a mistake. I just said I was going to differentiate that, so I have to make that choice. So I want to differentiate the log. So I'm going to take u equal to log of x. That means I have to choose v prime equal to x cubed. If I differentiate log x, I get the derivative is 1 on x, and the integral of x cubed, so the integral of that will just be 1/4 x to the power of 4. Alright, so I've set up for integration by parts. Let's just do it. By integration by parts, since they've nicely set notation for me, I'm just going to say I2. So it's going to be u times v. So I will get a quarter of x to the 4 times log of x. And I will need to subtract off the integral of u prime by v. So I'll subtract off the integral of 1 over x times a quarter x to the 4 dx. The first term is perfectly okay, I don't need to do anything with that. It's 1/4 x to the 4 log of x. This, well, I might just do it quickly in my head. This will cancel out with that to give me an x cubed. I already know what iterating x cubed is, it was right here. So I'll get minus a quarter squared times x to the 4. And of course, I did an integration, I need my constant of integration plus c. Maybe I should have cleaned it up to begin with, made it 1 over 16. I think I'm okay with that. So that is what the integration is. It's very simple integration by parts, you just need to spot what your choices are. So
I've got no trouble with that. I don't even think that's. I think that's fine.
Right. Okay.
Ball form.
Ball form. Yes. Let's see that one.
Maybe I can mention that after this question, Josh and I will take a short 5-minute break, get a cup of tea, and then we'll get on with question 4 of this paper. I encourage you to stick around if you're a MATH1131 student. The questions aren't overly complex. They will be a step up from what you've seen so far, but yes, please take a break yourselves, get a cup of tea after this question, and we'll all come back in 5.
Alright, so we have a curve and it's defined in polar coordinates. So I think the first thing I want to do is actually take that and get it back in, write it out in Cartesian coordinates. Let's see. So the first part, well actually let me just, before I even start with part A, I'm just going to write out what the where it is in Cartesian coordinates. So question 7, or part 7. So, well, let's just write it out. So x will be r times the cosine of theta, which in this case is going to be 1 plus the cosine of theta times the cosine of theta, and y will be sine theta, which will be 1 plus, again, the cosine of theta times sine of theta. Okay. So part A, we have to find the slope of the tangent to the curve at the point 0, 1. So this is 0x coordinate, 0x coordinate, 1 y coordinate. That quite clearly has to, well, I mean, this is always positive, so that has to occur when the angle is pi over 4. So, let's see, x, y equals 0, 1, when theta is equal to, well, theta must be not pi over 4, it's pi over 2. It's definitely pi over 2. So 1/4 of the way around the circle. I'll just quickly work out what the r coordinate is as well. So so cosine vanishes at pi over 2. So you'll just end up with 1 plus 0, I'll just get 1. Well, I may not need to know that particular value. Okay, so when theta is pi over 2, what is the slope? So there's a well-known formula for slope for a parametrized line. The slope is given by, so we have dy dx. You can calculate it as dy d theta divided by dy d theta, and that is equal to, so I'm just going to do a bit of a calculation. You take the derivative of this divided by the derivative of that. So, well, let's just quickly try and quickly do the derivative of 1 plus so it's going to be product rule. Derivative of 1 plus cosine is minus sine theta times sine theta. And I'm going to add on 1 plus the cosine of theta. Derivative of sine is cosine. So cosine theta. And I'll be dividing that by, no, typo. Sorry, that should definitely be an x. So I'll be dividing it by derivative of x. Right. So this will just be similar to before, minus sine theta, this time times cosine theta, and plus 1 plus cos theta. What's this one? Yep, derivative of cosine is minus sine, so times minus sine theta. Alright. So what is this? And what does this equal when theta is pi on 2? So at theta equals pi on 2, this is, so sine is going to be 1 and the cosine is going to be 0. So we just get dy dx is equal to minus 1 times 1 and something which multiplies to 0, so minus 1. This will be a 0 and I'll get a 1 times minus 1. I'll get a minus 1. So the slope is just 1. It has slope 1. Okay, which is something nice to know. So when we come to plot this, this will give me some nice information to put on the plot. Alright, so that's part B. So that's part A. Part B, we want to actually use this same information to work out when the tangent curve is horizontal. So when dy dx is 0. So I will leave up that equation, but I will erase the first part I wrote. Alright, so we'll need to look at the points. Well, firstly, let's just look at the points where this top part. Yeah, we just need to look for the parts where dy d theta is 0 for a start. So part B. So let's just say dy d theta. So I calculated that. It was minus sine theta sine squared theta plus. That's quite nice. You look at it, you get a cos. Oh, it's not quite as nice as I thought. You get a cos theta plus a cos squared theta. It would be easier for me to solve this, I think, if I wrote everything in terms of cosine. So I'll just replace this sine squared term with 1 minus cosine squared term to get a minus 1 minus plus cos squared theta plus cos theta plus again cos squared theta. So I get 2 cos squared theta. This isn't what I saw when I did this before. Plus cos theta minus 1. Let me just quickly verify that it's correct. So something cos theta, cos squared.
That's right.
That's right, okay. So yeah, we're going to try and find the points where this is equal to 0. And while that's quite nice, it is just a quadratic equation for cos squared. So dy d theta equals 0 when cos of theta is equal to minus 2 plus or minus the square root of 4, so it's 4ac, so it's become a plus 8. That's right. Did that 2 times 4 is 8, yep. So plus 8 over 2a, which is 4. Right. So that is going to be 8.
That's a 1. B is 1.
Ah, yes, sorry. I'm looking at 8 for some reason. Alright, so it's minus 1. Okay, thanks. Cool. So that's actually quite nice. So you have minus 1 plus or minus. So this is root 9. Root 9 is 3 over 4. And I'm just going to write this as, so choose positive 3 becomes 2 over 4. So 2 over 4 is a half. And the other choice is choose minus 3. You get minus 4 over 4. You get minus 1. Okay. I can't rub this out yet because there is an issue that will come up. So I will need to keep a track of this equation here. So I may just box
How
it.
about do that? Is that just too crazy?
That works.
Cool.
Cool, thanks.
We can bring it back later.
Alright, so we just seen that, yeah, so the cosine of theta had to be equal to 1/2 or -1. So if you look at that, cosine of theta is equal to 1/2. So I might just quickly line myself with a picture where I should expect this to be. Well, we're just looking at sine theta versus cosine theta. Yeah.
Just pi on 3 or pi 3.
Thanks. So, yeah, it's going to be this point. So cos theta is equal to -1 will be this point, and 1/2 is this point here. So this is, like you said, pi on 3, or minus pi, actually, that's not quite true. Well, this angle here is minus pi on 3, but the restriction is we are looking at theta between 0 and 2 pi. So if you take the cos of theta is equal to 1/2, you will end up with theta is equal to pi over 3, or it's going to be equal to 5 pi over 3. So just pi over 3 short of a full rotation. And the other case, when cos of theta was equal to 1, cos of theta is equal to -1, well, that's when you've gone halfway around, or theta is equal to pi. So we can actually just plug these into the equation. So our equation is here. So two of those points, they pose no trouble plugging them in. I guess I probably should just do that. So at
Josh, I think you were right. That is negative pi on 3. There's a typo in the notes. So it's not 5 pi on 3, it's negative pi on 3.
negative pi on 3. So I should use negative pi on 3?
It is, yeah, negative pi on 3.
Okay.
The notes say 5 pi on 3, but they're wrong.
Yeah. The range is.
Oh, okay, we'll adjust it to. Sorry, no, 5 pi on 3 is fine. Yep. Carry on.
Right. Right, so let's just quickly go through all the cases. So we have theta is equal to pi on 3. We can plug that in, so I already know that the cosine is going to be 1/2, and the sine is going to be root 3 on 2. So, well, actually no. Yeah, sorry, I guess I'm doing this wrong. I know the top vanishes, that's why I'm doing it. What I meant to just double check is what's happening with this bottom here. So this, yeah. Well, what's important is that when you do put in pi on 3, this bottom part doesn't vanish. You have a non-zero number down here, you have a 0 on top, so there's no problem. Yeah, so that one's not a problem, so maybe I'll just focus on. So yeah, well, I'll say that. Theta is equal to pi over 3, and 5 pi on 3. The denominator doesn't vanish. So dy dx equals 0 there. Unfortunately, if you just put in theta equal to minus pi, well, that sine term will vanish, as will this sine term, and the bottom does vanish. So we do need to be careful to make sure that we need to look at the limit in this case. So in this case, the top vanishes, goes to 0, the bottom vanishes, goes to 0. We'll just need to examine the limit in that case, and this is of indeterminate form, so it'll be very quick to just use. Yeah. So actually, my sentences are running together. That was a conclusion to the previous sentence. At theta equals minus pi, well, I'm going to consider the limit as theta, not minus pi, it should be pi. So as theta goes to pi of dy dx over, sorry, dy d theta, dx d theta, which is the limit as theta goes to pi. This is not so pretty, but well, not so bad either. Alright, so we had a minus sine squared, the derivative of that is a minus 2 cos theta sine theta. Derivative of this term, well, there's a cos theta and a cos squared, so cos theta goes to minus sine theta, and that last term, cos squared, will go to a, what cos is minus, so I get a minus 2 cos theta sine theta. Right, this next term, derivative, okay, product rule on this. Sine goes to cos, it's a minus cos squared theta. Cos goes to minus sine, it's a plus sine squared theta. This next term, well, just quickly do it. So it's going to be a minus sine and that's sine times the cos. In fact, I'm a little bit silly because I could combine these two into that one term to get minus twice those. So in fact, it should have been 2 lots of that. And next, that little part I didn't mention, derivative of minus sine will be minus the cos of theta. Alright, so we can just quickly go and plug this all in. So when theta is equal to pi, sine will be 0, cos will be minus 1. So this will go to 0, to 0, to 0. This will go to, no, this is going to be going to 1. This goes to 0. This term also goes to 1. So overall it becomes a 0 over a minus 2 minus 1, a minus 3. Well, it's non-zero, so it just is equal to 0. So this is legitimately a point where the gradient is 0. Unfortunately, to show it properly, we do need to look at the limit because, and I have, because I've been in such a rush, I didn't really explain that step properly, I guess. I should have said it was of indeterminate form, and I'm about to apply L'Hopital's. So that's a,
I think it's tea time.
yeah.
Why don't you just sketch the graph for?
Yeah, let's just quickly
Sketch the graph and I'll say some things about it and yeah, it'll be tea time.
Okay. So they gave us some nice information when we were doing this question. They showed us where this graph is going to have horizontal tangent points. You do think, I wouldn't bother trying to find the vertical tangent points, that's not part of the question. Let's see. And let's also just put some of the, let's look at what some of the values are doing. So I'm going to remind myself that r was equal to 1 plus cos theta. So just let's start at cos equal, theta equals 0. So we get 1 plus 1. So it starts out at 2. When we go halfway around, well, so once we get to pi on 2, theta has, cos has vanished, so it's just 1. So 1, so that's 1 point. We know over here it actually passes through r equals 1. If you go all the way around to pi, we'll actually get 1 minus 1. It goes through here. It'll also go through negative 1. 1. 2. Thanks. Right, let's just remember, so we saw at pi over 3, we had a, so at pi over 3 we have a horizontal tangent point. If we also plug it in, it just cos is also just a half. So this will be 1 point, this will just be 1.5 units out from the origin. So it's round about here. It has a horizontal tangent point. I won't, I guess I don't really want to have that solid that's on my main part. So we're going to go out here to so 1.5 out. There's another point, the horizontal tangent point, and I know that it actually comes in quite steep there. It comes in horizontally there. So using those pieces of information, I know it will come up here. Oops, not the best graph. We'll have a tangent point there. Come back down through here. Come in quite steep here. Also come out quite steep here. Over there, and I really should. I know the slope. Well, it shouldn't have a sharp peak. I kind of draw it there. It should come through a lot more smoothly than that. So it's a very rough plot of what it looks like using very limited skills. And I can use color. All right. Comments about this entire thing?
Look, I think there's a general method that's being illustrated here on how to draw a polar curve. Something I might mention before we even attempt to draw the polar curve is that this r is periodic in terms of in 2 pi. So r of theta is this thing, and r of theta is equal to r of 2 pi plus theta. So this thing, whatever it's going to be, is some kind of closed shape. They give you hints about how to draw it. In particular, they ask you to find the tangent somewhere, you know, a point on the curve, you know where it's horizontal. And it's going to be horizontal precisely when dy dt is 0. And it's going to be vertical when dx dt is 0. And I would actually, even though it's not part of the question, if you're asked to draw one of these things, find where dx dt is 0, and that will give you these horizontal kind of points, and there's one here as well. And will give you this kind of shape. So once you know the horizontal and the vertical points on this graph, or the places where the tangent is vertical and horizontal, and maybe a few points on it, you can kind of piece together what this thing must look like. So if I knew that was horizontal, I know it's flat up there, flat comes in there, comes out there, and I know it's a closed curve, then I can just kind of join the dots, if you like, and make sure things are smooth where they need to be smooth. So this question really does walk you through most of the parts of how to draw this thing. It's debatable whether or not you need to do the vertical points where the tangent is vertical as well. I would have done that, maybe. The question doesn't explicitly ask for it. This is a harder question, I think.
Yeah,
There's a lot in this.
Especially that one point. This is a tricky point to verify.
That is quite brutal.
Yeah.
Cool. All right, we're going to take a short break and come back for question 4 from MATH1131. Oh, and if you're out there waiting for me to attend my exam consultation, I'm going to be in here doing my exam consultation. So I'll put a little note out on my office. Cool, we'll be back in 5 minutes.
What was that? It just looks like that. It's fine. I'll put a little note on there saying packing fine.
Let's get some tea. Right. I feel better already. We haven't even. I don't know, something about making tea that is just nice. I haven't even drunk the tea. It's just,
Might be something nice about walking out of the room.
yeah, there's something nice about that too. Stretching the legs. All right. Hmm. Oh, is the water made it like really sticky?
We would slide.
Okay, well, good. Won't slide. Awesome. Extra secure. Oh, right, yeah, I see what you mean. Okay. Cool. So, welcome to the higher version of the stream now. So as is tradition, I will write out what time I intend to finish this. So on my watch, it's 5 minutes past 2. So I would finish this at 2:35. But of course, we're not going to manage to finish that in time. It seems like we're going at least half the speed you would normally go in a real exam. Right. So my question: find the shortest distance from a point to a line. You can 100% expect a question like this in your exam. This is a projection question. I will draw for you. The drawings are always the same. Please don't try and do this to scale or something crazy like that. Just draw a little picture to make sure you get your vectors in the right spots. So here's a line, here's a point. I have no idea if this is going to end up being what the actual answer looks like. Here's my point P, here's some point A, which is a point on the line, and I'm going to I'll get some colour. So I know P, I know that's the point 1, 2, 0. I know A, a point on the line, is 1, 0, 1. And I need to find the shortest distance from the point to the line. Let's call this thing here Q. Q. Right? Here is the point Q. So the shortest distance from the point to the line is this perpendicular distance here, PQ. So I have to find this point Q on the line such that PQ is perpendicular to the line. How's he going to find this point, you say? Well, allow me to show you. I need to construct one more thing. I need this vector here, AP, and I might do this in red. I need the direction of this line here, which I'll call V. And I might just write down here that V is equal to the direction of the line 0, 1, 1. Like that. Right, so part of this question is just knowing how to construct this as a projection question. The projection of AP onto V gives you this vector here, AQ. It's as if there was some sun infinitely far away and the shadow of AP onto this line gives you, where that shadow finishes is the point Q. So projection, which is AQ, that is the projection onto V. So you're projecting onto this direction the vector AP. So this is only going to give me AQ. Now actually what I really want is that. But we'll get there. First of all, the projection. I need to calculate AP. AP is P minus A, so that's 1, 2, 0 minus 1, 0, 1, which is 0 to negative 1. Good. So this projection then is AP. Remember, it's a scalar multiple of V. The scalar multiple is in particular AP. So I'll do it like that. Dot V over V squared in the direction of V. Which is, so I'll just write this out. 0 to negative 1 dotted with V, 0, 1, 1. Divided by the length of V squared, so that's 2 in the direction of V, 0, 1, 1, is equal to, well, this is 2 minus 1 is 1, so this is half V. AQ is half V. Good. So really, if I want to just adjust my diagram accordingly, you don't have to do this. I'm going to do it because I've got a whiteboard. I can just rub things out with my finger. That's what V looks like. And AQ is just half that vector. Like that. So this is just to bolster what my image here. Good, so what I really want is the length of PQ, and I can get it because I know what AQ is and I know what AP is. So AQ, or the length, sorry, of PQ. So from P go to Q, well, I can do that as the length of from P go to A, which is negative AP, so that's, I'll write this as from P go to A plus A go to Q, which is equal to the length PA is negative AP, so that's 0, negative 2, 1, plus AQ, which I found out was half V, so that's 1/2, 0, 1, 1. And this is the length. Maybe I'll take a common factor of 2 out of this. 0, negative 4, 2, plus 1, 0, 1, 1, which is 1/2 times the length of 0, negative 3, 3. Have I done this right? I feel like I've made a mistake somewhere. Well, I'll just keep going. So this length here is the square root of, yeah, I think I have made a mistake somewhere. Did you see it, Josh?
No. So, what answer were you expecting?
I'm expecting root 3 on 2.
3 on 2. Oh, you're adding 2. No, isn't that correct? Because that length is root 6? No, that would be root 3 on root 2, wouldn't it? Yes, that would be. Let's go through calculations. That's that is what you had. But you end up with root.
This is, I know this is correct. I've just messed up here somewhere.
I mean, length. Yeah. Is that correct? Probably root. Length that is root 5.
Is it?
Yeah.
Oh, well, let's just go with this then. I'm just going to say that I think the answer is this. So that's the square root of 0 squared plus 3 squared plus 3 squared, which is, so that's 2, so 3 over 2 root 2. Yeah, I can't, there we go. I think I might have made an error in here somewhere, but look, this is the algorithm. Hopefully, maybe someone in the comments can point out where the error is, if there is in fact an error. Right. Actually, Josh, could you look up the notes and just tell me if that's the right answer?
Where is the book?
Good question. Maybe Norman's taken it. Never mind. Let's just go on.
Here it is.
Is anyone in the comments?
Actually, your answer is correct. What you
This-
wrote on the board.
Oh, this is correct. Oh, well, there I am worrying about nothing. All right. Maybe I should actually drink some of that tea. Just making it wasn't enough.
The chat wants to know whether it's white or black tea.
It's what is this tea? This is it's a licorice tea made of mint and what's that vegetable that tastes like licorice?
Aniseed?
No, There's some vegetable that tastes like licorice.
Well, I'm not aware of it.
Ah, what is it? I'm obviously not firing on all cylinders here. I can't even remember the name of a vegetable. Alright, so clean this up some. Fennel. Fennel. Mint and fennel tea, chat.
Was it fennel?
It is fennel. Yeah. The chat is like, yeah, it is fennel. Thank you, chat. I did remember that by myself. Right, tea. Good. Part 2. It's got 2 parts, A and B. Use the dot product to prove this. This is not a particularly tricky question, it's just large. So I'll start with the left-hand side. Question, so this is 2A. Well, by the way, writing something like this is nice. Be nice to your marker. Let them know what question you're doing. Your marker is searching for this information, so please put it up there. Your right-hand side. Left-hand side. My goodness. Left-hand side is equal to that stuff, which I will write as A plus B draw a whiteboard. A plus B dotted with A plus B plus A minus B dotted with A minus B. Right. That's the right hand side because the length of a vector squared is the vector dot producted with itself. And now I'm just going to expand this out. So this is A dotted with A plus B dotted with A plus B plus A dotted with A minus B plus negative B dotted with A minus B. Here I'm using the fact that the dot product is linear in the first term. So this product here, A dot B dotted with anything, splits up as A dot thing plus B dot thing. And similarly over here, A minus B dotted with anything splits up as A dot thing plus minus B dot thing. It's linear in that first term. It's also linear in the second term. So now I'm going to expand this thing here out as A dot A plus A dot B plus B dot A plus B dot B plus A dot A. I'll write this as a plus. It's plus A dot negative B plus negative B dotted with A plus negative B dotted with negative B. Maybe you can't see that. I'll just write it down here. Plus negative B dotted with negative B. Negative B, like that. So, my dots. The good news is lots of stuff cancels. So this B dot A cancels with negative B dot A. Maybe I'll write this out one more time before I start cancelling things. A dot A, that's just length A squared. And here's another A dot A, so I get 2 of those. Here's a B dot B. I might leave that as B dot B for the moment. Oh, sorry, I'll leave it as length B squared. This is A dot B. A dot B and B dot A are the same, so I'll say this is 2A dot B. Here I've got an A minus B, and I can take scalars out of this. So I can write this as negative A dot B, and I can take the scalar out of this term as well. So I get negative 2A dot B, and this thing here becomes positive. I take the 2 scalars out. I take a negative out of this one and a negative out of this one to give me positive mod B squared. And as you can see, that will add nicely with that. Those 2 things will cancel, and I get left with twice length A squared plus twice length b squared. Like that. So this is not a long question, oh sorry, this is not a hard question, but it is quite long. Josh, do you have a comment about this?
I guess just one notation comment. I would have put brackets closing off these two things.
Okay.
Because personally, it looks a bit funny to me. It was like vector plus scalar plus vector. So just if I saw that, I know what you mean, but
so Josh
clarity.
Josh is suggesting this for clarity, and I agree. That's a good idea. Thank you, Josh. And this is the right-hand side. Good. For part B, this is just a word question. Consider a parallelogram if A and that. So if I have, that should be B, B. If A is this vector and B is that vector, describe geometrically what this means. So B, this is saying that the diagonal length squared, that diagonal, plus this diagonal BD length squared is equal to this length squared plus this length squared, so that's the two length A's, this is also vector A, plus this length squared plus this length squared. What it's telling you is that the square sum of the diagonals is the square sum of the perimeter of your parallelogram. This is also known as the parallelogram law, so you wouldn't be expected to know this, but just since we're here. This law will hold of parallelograms in nice spaces like what we have here. So any words you might say about interpreting this result in terms of a parallelogram and square lengths, that would probably get you the marks. Josh?
Yeah, that's nice. I guess you could try and also, as an intermediate step, write down which of these edges this corresponds to. So you can see that A plus B is the edge AC. So just to remind yourself, okay, that's what I'm calculating there. This one, A minus B. I guess that is final minus initial. That would actually be DB, but since you're taking the length and squaring it, you're not going to be able to tell the difference between BD and DB from that point of view. And yeah, I think you have to look at this and just give it a bit of thought to see what it's saying. So the fact that you're actually taking twice the length squared, I wouldn't say it. It's more natural to interpret it as actually these two, the square, the sum of these two edges, the square of the lengths of those two edges. Something that it's not as nice as it's stated there. Right. But yeah, I mean this calculation, it's nothing tricky, but you do need to push through it and get it correct. And you know what you're aiming for, so you should be able to get it correct.
And they do give you a hint about this dot products and length squared. You should know that relation.
Yeah.
Right, your turn.
Okay. Alright, so here's another one involving sines and, well, just sines actually, and cosines, but it won't be as hard as that last one I looked at, thankfully. So the question starts off by telling us what to do. We have to use Moir's theorem to express the sine of phi theta as a polynomial in sine theta. So I might just quickly say what Moir's theorem tells us.
Good plan.
So in this situation, so D, oh, a bit wet still. So, I'm not going to say the general theorem, I'm just going to say the one that I need. So the Moir's theorem in this case tells us that if you have, take cos of, well, I'll write it this way. So it's the cos of phi theta plus phi sine of phi theta. That is the same number as if you calculated just the cos of theta plus I sine theta all to the power of phi. So I just need the imaginary part of this, and I will have a nice relationship sine phi theta and things in terms of coses and sines, and a little bit more work will give me just sines. Alright, so we're going to have to expand this. I'll have to remember this is just going to be a binomial expansion, and to make sure I make no mistakes, I'm going to put down Pascal's triangle. Right, so I think we should all be familiar with this, that each term is just the sum of the two terms above, with ones down the edges. So 4 and 1 is 5, 4 and 6 is 10, 6 and 4 is 10, 1 is 5, and 1. So I need this row just to get my expansion done correctly. Okay, so let's just start expanding. So I'll have a 1 times this term to the power of 5, a cos to the 5 theta. I'll have a 5 cos to the 4 theta, and an I sine theta. Next term we'll have a 10, so a 10 cos cubed theta, and an I sine theta squared. Alright. So I'm not trying to take care of those squares of I yet, I'll do it a bit later. Get a 10 cos squared theta times I sine theta cubed, that'll be a 5 times cos theta I sine theta power of 4. And the last term, I have a I sine theta to the power of 5. Now, I'm just going to grab the imaginary. Part while I'm here. So I will just note that this. Actually, let's concentrate on the parts I like, the parts I want. This will be purely I times something real. This is going to be purely real. This will be part of the imaginary part, and so will that. So I'm just going to pull these out and do the simplify as I'm going. Comparing real and imaginary parts. Get. So the comparing, I don't care about real, I just want the imaginary part. So comparing imaginary parts, we get, this side will just give us the sine phi theta. If I look here, I will have a 5 cosine to the 4 and a sine. That I is just an I. Yeah. So I get a 5 cos to the 4 theta sine theta. I have to be careful with this term. It will have an I cubed. I cubed is minus I. So maybe I'm going to be doing this a little bit quickly, but I will get a minus 10 cos squared theta sine cubed theta. And the final term will have a, well, this will be I to the power of 5. That's 2 minus 1's. So minus 1 squared is 1, so I'll just end up with a plus sine to the 5 theta. Now I do need this purely in terms of sine theta, but that can be nicely expressed in terms of sine theta, as can cos squared. I'm going to leave it just written out in terms of sine. I guess I could borrow that notation next up there to make my life easier. Actually, maybe I will do that. So this will be 5. So this is cos squared squared. Cos squared is 1 minus sine squared. I'm squaring that. So I am borrowing this notation. And I'm going to multiply that by sine. Minus 10 times 1 minus x. So 1 minus sine squared. Sine cubed. Plus sine power of 5. Now, it is given in the question. I might just put a comment over here. X equals sine theta. Just so it's all clear. Alright, so 5 times 1 minus 2x squared plus x to the 4 times x. Let's just expand this. A minus 10x cubed. A plus 10x to the power of 5 plus x to the power of 5. Let's just grab all the highest powers of 5. So I'm going to have 1 from here. So 5, a 10 and a 1. It's a 16x to the power of 5. There are some cubic terms in sine. There's a minus 10 and another minus 10. So I get a minus 20x cubed. And finally, there is only one thing linear in sine. It's a 5 sine. So I get a plus 5x. So that is sine to the 5 theta in terms of sine theta, which I've given you the notation of x. Okay. Now, you can see that they've put us in a nice position to answer part B, because I do just see exactly what I found right there. So I just need to know when this entire thing, well, when this is equal to 0, it means that this first part here is, of course, equal to 1. So when sine of 5 theta is equal to 1. So I don't really need to see any of that to answer this next part of the question, so I'm just going to erase it. Find the eraser. Okay, so the important part is this first part here is actually just sine of 5 theta. Here x is sine theta. Okay, so B, consider this polynomial and just show that sine of 10 over pi is a root of that polynomial. So you can see this is just going to follow quite quickly from part 1. So from part A, well, you have that if x is just going to be the sine of 10 over pi, then I'll just write it this way, that 16x to the 5 minus 20x cubed plus 5x. Well, I know that was actually just equal to sine of 5 times the argument of, well, it's just sine of 5 theta. Here theta is equal to pi over 10. So it's just going to be the sine of 5 times pi over 10. In other words, the sine of pi over 2, sine of pi over 2 is 1. And that's just the first part. So hence, p of x is going to be equal to, well, we know what this is. This is a 1. The final term is a minus 1, which is 0. I guess, yeah, so it's a root. Actually, I should probably write it a little bit differently. So i.e. p of sine pi over 10 is equal to 0. So yes, that is a root here of this equation. So part C, they've given us the factorization of this into, well, they've given us the factorization of this polynomial into a linear part and the square of a quadratic part. And it says that we can, well, it says using the fact that this is how it factorizes, find the distinct roots. Well, all I need to do is really find what the solution of that is, and I can solve it, I think, quite easily using the quadratic equation. So this will vanish when either this first term is 0, so x is 1, or when that is 0. Okay. So, right. So, well, I guess it's using factorizing. So the roots are they're either going to be when this vanishes, which is x equals 1, or they're going to be when the second term vanishes, and that will be x is equal to, being careful, minus 2 plus or minus the square root of 4, so the term squared, minus 4 times those two will become a plus 16, dividing by 2a, so dividing by 8. Well, that's nice, it's all real, complex solutions, which is minus 2 plus or minus root 20 over 8. So that is, well, minus a quarter. 20 is 4 times 5, so pull out 2. So that will just give me plus or minus root 5 over 4. Right. So those are the roots. And these are actually double roots. So it is those factors do appear twice in this because you're having a square on this one. So those are the roots of this equation. X equals 1 and x is equal to that. Okay. So the last part is pretty much draw this all together and evaluate the sine of pi over 10. We have really worked out the sine of pi over 10. And, well, the way we're going to do this is we know it's one of the roots of this equation, and there are a few obvious ones which it can't be. Sine of pi over 10, that has to be between 0 and 1. It can't be all the way to 1, that would be pi over 2. So we can rule out this option, which means it has to be one of these two options. And one of these options is negative, so it has to be the positive one. So I'll just say that. So since, well, yeah, clearly that sine pi over 10, it's going to be greater than 0. It's going to be less than 1. So the only root above, oops, so the only root above it could be is the following. It's one we choose the positive sign. It's minus a quarter plus root 5 over 4. Root 5 over 4, well, that's somewhere between 2 and well, it's a bit greater than, root 5 is a little bit greater than 2, but this does come out positive. So yeah, that restriction means I must take this to be my, that must be what sine of pi over 10 is, which is a really nice number. Kind of surprising. Any comments, Daniel?
Only that even if you didn't manage to get all of part A, you can probably still manage to do some parts of the later questions as well. I think that's
Yeah.
important to remember. So don't just give up because you got lost somewhere in part A and it fell to pieces for you. You can pretty much carry on with this question as from that statement there.
Well, definitely, well, if part B is true, part C, you can always do. You can always find the roots of that, and then if that is true, part D you can do. So you can salvage things. If there's
And the questions will be designed like that, so you will be able to salvage as much as you can. Cool. This question. So we're getting towards the end of things, which is good. So you will have seen ways of calculating the determinants. You can expect a question like this and in your exam. And I want you to have a certain style when you do these questions. So anyone who's in my algebra class will have seen this already, but if you haven't been in my algebra class, then this might be new, and I want you to pay particular attention to the style in which this is done. We know determinant A, the determinants of B and C will be related to the determinant of A in some way. We're asked to find the determinant of B, and I'm going to write it like this. So this is IV, let det of B be equal to D, and then I'm going to write D is equal to the determinant of D, E, F, A, B, C, D minus 3A, E minus 3B, F minus 3C. Good. And then I'm going to slowly mold this determinant until it looks like the determinant of A. So I'll use my elementary row operations to slowly transform this quantity, the determinant of B, into a determinant of A. And I'm writing D here because some of my row operations will actually change the determinant. So I'm going to keep track of all my changes over here and the matrix over here. The first thing I'm going to do to mold it slowly towards A is swap those two rows, because I want the A, B, C on the top and the D, E, F on the bottom, and I've got the wrong way around it here. So I'm going to do a row swap, row 2, row 1. Swapping rows will negate your determinant, and I keep track of that by saying negative D is equal to A, B, C, D, E, F, then I'll do a row 3 is row 3 plus 3 row 1. And I'll get negative D is equal to A, B, C. I should mention this kind of row operation here, row equals row plus some constant times another row, does not change the determinant. So this is still negative D over here. D, E, F. And this is just D, E, F. And then I'll do a row 3 is row 3 minus row 2. Again, this kind of row operation does not change the determinant. I've still got negative D is equal to A, B, C, D, E, F, 0, 0, 0. The determinant of any matrix with a row of zeros in it, like this, 0. Determinant of a square matrix that has a row of zeros in it is 0. So negative D is 0, hence D is 0. You might have been able to see this straight up, that D was going to be 0. Great, if you can do that, sure. What I want to emphasize in this question is this particular way of answering these questions, where you let the determinant be equal to something, you say D is equal to this, and then you transform this into, well, hopefully A, using step-by-step row operations. And you keep track of how your row operations have changed the determinant using this little tool here, this D equals business. So this is useful too. Good. I'll do the determinant of C now. So I'll just run most of this stuff off. Notice that C isn't exactly what I was expecting. I was expecting something like G, H, I, and then an A, B, C, and then a G, D, F, but I've got instead the transpose of that. Fortunately, the transpose of C has the same determinant as C.
The students are suggesting a different notation than D, since D is already in the problem.
Thank you. Cool suggestion. Shall I just call it det C then? So I won't make that. I won't make that. I will just say, since det of C equals det of C transpose, we could just say det of C is equal to exactly that, the determinant of C transpose, which is G minus 3A, H minus 3B, I minus 3C, 2A, 2B, 2C, A minus D, B minus E, C minus F. Here I just have the determinant of C transpose. And this I can mold into A by step using my row operations. Maybe I'll start by multiplying row 2 by half. So row 2 equals half row 2, like this. This row operation will change your determinant, and it will change it by half. I'll keep track of that by saying 1/2 det of C transpose is equal to G minus 3A, A, B, C, like that. Let's see. Maybe I'll do a row. I want this on the top. I want that up there. So I'm going to have to do some row swapping here. Row 1 swap with row 1 swap with row 2. I want that ABC up the top. Row swapping will negate your determinant. Okay, I kind of want my G, H, and I down the bottom, and I want my D, E, and F in the second row, so I'll swap those two again. I'll swap row 2 with row 3. And I'll end up with negative half det, so I'm back to positive half det of C transpose is equal to A, B, C, A minus D, B minus E, C minus F, G minus 3A, H minus 3B, I minus 3C. I hope you can see what I'm doing here. I'm slowly making this matrix look more and more like A, and I know the determinant of A is 7. So I've got my A's where I want them, I've got DB's and D, E, and F where I want them, the G, H, and I where I want them. I need to clear out this other stuff. That won't be too hard. just leave that there, and I'll do a row 2 is row 2 minus row 1. And I get unchanged determinant on the left, 1/2 det of C transpose is equal to A, B, C. This is negative D, negative E, negative F. And I'm going to add 3 times row 1 to row 3. And this is, again, this operation does not change the determinant. I get 1/2 det of C transpose is equal to A, B, C, negative D, negative E, negative F, G, H, I. I'm almost there, I just need to multiply this by -1. Multiplying a row by a constant will change the determinant by that same constant. So we say row 2 is negative row 2, we're obliged to multiply through by the -1. So I'll write that as -1 times that. Is equal to A, B, C, D, E, F, G, H, I, which is the determinant of A, which is 7. Hence, I can just multiply through by -1/2 to determine that determinant of C transpose is equal to -14, and so det C also. So the determinant of C is -14. Please just be aware of the row operations and how they affect your determinant. Row swapping will negate the determinant. Row operations like this, where row is equal to same row minus a constant multiple, a multiple of some other row, doesn't change it, and multiplying through by a constant will multiply the determinant by that same constant. Those are the only 3 elementary row operations. You've just seen how they affect the determinant, and you can keep track of those changes using this kind of mechanism. Cool. Josh?
Yeah, no, I like that. Yeah, so I do like that, starting from the what you have, trying to get back to where you start. Especially because you didn't actually end up back where you started for B.
Yes. Look, if you saw that, this has got a row of zeros in it, sure, but I maintain the method is good, which is why I did it using the method anyway, even though I knew the determinant would be 0. Yeah.
But no, so yeah, that's a really good method. Okay, so
One more question?
one more question. So there's one more question there. It's actually quite a short question, despite how it looks.
Awesome.
Okay. So yeah, a lot of words in this question, but most of it's actually just set up to help you. If you look at the question, it actually starts by telling you things that you'll need to know to answer this question. So it says, recall that the dot product of 2 vectors can be written as A transpose B. So this is actually the matrix product between a row vector and a column vector. And it also reminds you that an orthogonal matrix is one of the following ones. We have Q transpose, Q is the identity. So yeah, so it's a little bit more setup. That Q is going to be an n by n orthogonal matrix, satisfies that, and V a non-zero vector in Rn. So first part, prove that V and the matrix, the vector multiplied on by Q, actually have the same length. So it's actually, well, if you just look at what they're telling you, they're reminding you this and reminding you this for a reason, is that if you look at, the length of QV, if you look at the length of QV squared, it's good to remember that that is actually just the dot product of QV. with itself. And they remind you that this is actually just going to be the same as Q V transpose multiplied onto QV. So, importantly, the transpose of a product is actually just the product of the transposes, but you have to remember the order flips. So this is the same as V transpose Q transpose. So I'll just turn them around, transpose them both, Q, V. I like to give reasons while I'm going, so I'm just going to write down that that was the transpose of a product. Well, we know that Q is orthogonal, so we know what this quantity is. This quantity is just the identity. So we're going to end up with V transpose times the identity times V. I might just also add that reason. They tell it to you, but let's just put it in. So Q is an orthogonal matrix. And finally, well, because that's the identity, it doesn't do anything to V. So V transpose V. It's complete, it's V dot V. It's the length of V squared. So we've shown that the length of this thing squared is the length of that thing squared. Because these are both the length of a positive number, you can conclude that hence the length of QV is actually equal to the length of V. So it's a cute algebraic proof that the length of QV is the length of V. And it just relies on you knowing how to take the transpose of a matrix product. So part B is to show that if the vector is a certain, well, if this non-zero vector has the property that when you multiply it by this matrix, you just get some scaling of the vector. There's only two possible ways that can happen. There's only plus or minus one. You can either have lambda, you can either have QV as V, QV is minus V. So we just need to show that. So, well, let's just follow through, see what happens. We look at this. So, right. So note that, well, lambda times V. So the scale of the length of this vector here is actually just, well, it is the absolute value of lambda times the length of V. Now by hypothesis, by the setup in the question, this is actually just supposed to be equal to the length of V. And we know that Q doesn't change V, so it is just the length of V by part A. So, yeah, we have this number, which is the length of lambda, sorry, the absolute value of lambda times this number. It's promised to be non-zero. Has to be equal to just the length of the vector, so we can just divide through by the length of the vector and get a relationship for lambda. Dividing by the non-zero length of the vector gives, well, it gives that the absolute value of lambda is 1, and that only has two options. So hence, lambda is equal to plus or minus 1. So yeah, nothing. It's actually quite an easy question. Despite all the words that are on the page, they set up a lot for you. You just go through and yeah, it's actually fairly simple. Any comments on this?
It's fairly simple if you're comfortable with matrix algebra. So I think that's nice. Mentioning that the quantity you're dividing through by is not zero, that's important. There will be some questions where, in fact, this is quite critical. So be careful when you're dividing things to make sure they're not zero. This is a real, lambda is given to you as a real number, so certainly the only two possibilities are lambda is plus or minus 1. That's fine, I would have accepted this in the final exam. It's a good answer. Cool. Well, that's it from us.
Right.
Any last words, Josh?
No, I guess good luck.
Final exam tips? get a good night's rest before your finals.
Yeah, make sure you're not rushing to get there. There was a Moodle post giving you a set of advice on the final exam. Mostly just make sure you do your work in all the separate booklets and so forth. So obvious things, but yeah, sleep is very important. You don't want to.
You want to perform on the day, so make sure that you're well rested. The preparation you do for this exam will be the days prior to the exam day. So don't make sure that on the day itself you're just physically comfortable and you've had a good night's rest, had a good meal, cup of coffee.
Or several.
No, not for me.
Yeah.
Cool. Well, thank you very much. We'll see you guys in Math 1B. All things going well.
Cool. All right. Well, see you next time.